For question number 1, the answer is answer choice number 2, a line reflection. The reason why it is not a rotation is because if you take this triangle and you rotate it this way, A is going to match up to E. B is going to match up to D. But if you take a look at the letters here, A is supposed to match up to D. A is not supposed to match up to E. B is supposed to match up to E. B is not supposed to match up to D. So just churning ABC, just rotating it, will not make the letters match up. The answer here is a line reflection. And the reason that it is a line reflection is because if you flip these points over the line of reflection, they match up to where they're supposed to. A is supposed to match up to D, B is supposed to match up to E. In order to see what the line of reflection is, I'm just going to connect as best as I can. Two corresponding pre-image and image points. And I know that B and E are supposed to correspond. And really quickly, just to make this as accurate as possible, I'm just going to construct the perpendicular bisector in order to get the line of reflection. No, you did not have to do this on the test in order to answer the question. You could have just drawn a perpendicular line in order to see visually the line of reflection. Oops. And over here, we have the line that this triangle was reflected over to get this triangle. If you flip this point diagonally over this line, it will match up to D. If you flip this point diagonally over this line, it will match up to E. Moving on to number 2. Let me get rid of this over here. We're looking for the transformation that's not going to map the square onto itself. So the answer does end up being answer choice number 1 because the y-axis is not a line of symmetry of the square. If you check out the other answer choices, the x-axis, that is a line of symmetry. The line the line y equals x minus 1, answer choice number 4. I'm going to start with the reflections first. That has a y-intercept of 1 and a slope of negative 1, and a slope of 1. And as you can see, this is a line of symmetry of the square as well. Answer choice 3 is a rotation of 180 degrees around the point 1, 0. Here's the point 1, 0. Notice that is in the center of the square. So if you do rotate the square 180 degrees or even 90 degrees around this point, it will map exactly onto itself. So the correct answer choice is answer choice 1 because the y-axis is not a line of symmetry. Moving on to number 3, we need to find when the decagon is going to look like itself. It's a rotational symmetry question. A full rotation is 360 degrees, and a decagon has 10 sides and 10 angles. So the minimum number of degrees that we need to rotate this decagon by to make it look like itself is 36 degrees. That's not an answer choice here. So you do have to go through the list and see which of these is a multiple of 36. If you divide each of these by 36, only one of them will give you a whole number. You can see which one that is for yourself. Question number 4. So we have a scale factor of 0.5 or 1/2, and that means that the shape is getting smaller after the dilation. So the original shape is bigger than the new shape because this was a reduction. So the original shape is double the new shape. For example, if we just consider a line segment, right? And let's say the original line segment is 4, has a length of 4. And then we dilate it by a scale factor of 1/2. It would now be 2. So as you can see, the original is double the dilated one. And that's what's happening here. The original is double the dilated one. Answer choice 3 is the one that says that. It says that an original side of this triangle is double the dilated side of the triangle. Answer choice 4 says it the other way around. Answer choice 4 says that the original side of the triangle is half of the new one. But that's not true. That would be if there was a dilation by a scale factor of 2. But since it's a dilation by a scale factor of 1/2, since it's getting smaller, the new one would actually be double. Sorry, the original is double the new one. The reason why answer choices 1 and 2 are not correct is because when you dilate a figure, or when you do any transformation to any figure, the angles don't change. That's because dilations produce similar figures. Similar figures have different side lengths because they're different sizes, but they have congruent angles. None of the transformations change angle measure. The other 3 transformations, rotation, reflection, and translation, make congruent figures that have the same sides and the same angles. But dilations do not change angle measurement. Similar triangles have congruent angle measurements. And that's why 1 and 2 are incorrect. Nothing's happening to the angles. They're remaining the same. And question number 5. Which statement is always true? BC congruent to EF. Here's BC and here's EF. Do they correspond? Yes, they do. So these will be congruent after a reflection because reflections produce congruent figures and these sides correspond. So answer choice 1 is the correct answer. Answer choice 2 is not correct because A does not match up to F. Angle A is here, angle F is here. Angle A matches up to angle D. Answer choice 3 is not correct because side AC and side DE don't correspond. Side AC corresponds to side DF. And same thing for number 4. Angle B doesn't correspond to angle D. Angle B corresponds to angle E. The rule for reflecting over the line y equals x is to change the order of the coordinates. So I'll write that down over here. If we're reflecting over the line y equals x, the original coordinate is going to switch order. You can pick the correct answer choice now with that in mind. For question number 6, the first thing that we have to do is take the equation of the line and put it into y equals mx plus b format. So I'm going to subtract 3x from both sides. And then I'm going to divide the whole equation by -1 in order to get y by itself. Now remember, dilations preserve parallelism, and parallel lines have same slopes. So nothing's going to happen to the slope. We are centered at the origin here. So we can use the rule for figuring out the new y-intercept. And the rule is that we're going to take the original y-intercept and multiply it by the scale factor. So you can take -6 and you can multiply it by 1/2 to get the new y-intercept. Your slope will still be 3. So it will be y equals 3x. And you need to figure out what the new y-intercept is going to be. This question over here was a bit tricky because we don't have a grid. And remember when we did a question like this on the review sheet, we spoke about describing transformations to the best of our ability without making anything up. The first thing I want to talk about is that this is going to be a rotation and a dilation. I know it's going to be a rotation because this triangle needs to turn to become this triangle, right? We want to make y come over here to v because y and v match up. We want to make x come over here to u because x and u match up. So we need to turn the shape, which is a rotation. And then we need to dilate it because we need to make it bigger, right? These are clearly different sizes. We need to make them the same size. Some people said reflection, and I just want to talk about why a reflection does not work. If you reflect, and let's just say you reflected over that line that I drew, mirror image of x is over here, mirror image of y is over here. So then, if you slightly turn it, x would match up to v, but x needs to match up to u. Y would match up to u, but y needs to match up to v. So a reflection wouldn't in itself make it have the correct orientation, and that's why a reflection was not the correct answer here. So we are going to be rotating and dilating. It doesn't matter the order, and we're going to try to describe as fully as possible without making anything up. So if I'm describing first my rotation, I need a center of rotation, and I also need a direction. So these triangles are both attached at point Z. So notice how point Z stays in the same spot when this becomes this. So point C would be a good center of rotation because then the rest of it would spin, would rotate around this point, but this point would stay where it is and everything would just rotate around this point. And the direction is a clockwise rotation. Well, you could also say counterclockwise because you could also go this way. I'm going to say clockwise because that's the shortest distance. So I'm going to write here a rotation, a clockwise rotation centered at point Z. And then I need a degree measurement. But I don't know exactly how many degrees we're rotating this by. Some people are at 90 degrees, but what if it's 89? What if it's 91? I don't have a grid. I don't have coordinates. I don't know for sure. So what we're going to do without making up a degree measurement is we're going to try to tell the person reading our response when to stop turning the shape. Because that's the purpose of the angle, right? We need to know when to stop turning the shape so that it aligns to this one. We don't want it to stop turning here or to stop turning here. We want it to turn and match up exactly to this one. So I'm going to use the language of the question in order to illustrate that. So I'm going to write to rotate it until xy is parallel, oops, that looks messy, to VU. And I think that's the best way of describing it because right now the angles aren't going to match up because these are different sizes. So when I rotate this, I'm just going to do a really bad sketch. Let me make that a little bit better. When we rotate it, this is how it's going to look right now. So the best way I can describe when to start rotating is when this base of the small triangle is parallel to the base of the large triangle. Because if we move it more, they're not going to be parallel anymore. So that kind of tells me when to stop rotating. Now I need a dilation. Dilations also need a center. So the center is once again going to be Z because we just want it to get bigger, but we want this point to stay put, right? It's already in the right spot. So if that's our center of dilation, it's going to remain unchanged. Everything else is going to get bigger, but the center is going to remain unchanged. So dilation, centered at point C, and I also need a scale factor. By a scale factor of, and I'm just going to describe the scale factor as a side of the image over the corresponding side of the pre-image, because that's how you find scale factor, right? If this is 2 and this is 4, I can take the image and divide by the corresponding side from the pre-image to get the scale factor that happens. Another way that you can describe it is you can say dilate until the angles match up, just like it says in the question. Until angle X matches up to angle U, is congruent to angle, matches up to angle U, and until angle XYZ matches up to angle UVZ. I'm going to include that as well to make my head super complete. So that angle X matches up to angle U, and angle XCY matches up to angle UZV. Moving on. There were multiple transformations that could have worked here, but the one that I saw most often was to start off by rotating this 90 degrees clockwise. And I'm just going to take a second and do that. Oops. So hard on the computer. And now let's check out the orientation. So A needs to match up with D, and A does match up with D. B needs to match up with E, and B does match up with E, and C matches up with F. So we're all good. The last thing we need is a translation. So I'm just going to use points A and D to figure out how far it needs to be translated. So that is 1 unit to the right and 4 units down. So I'm going to describe this. A rotation 90 degrees clockwise, centered at the origin, and right here at the origin, followed by a translation, 1 unit right, and 4 units down. There were other ones that worked as well, but this is the one I saw most often. Over here, we are dilating, and you do need to do this with a compass. And our scale factor is a scale factor of 2. Let me just move the compass down. Okay. Now remember that the center of dilation, the pre-image point, and the image point are all collinear. And when you have a scale factor that's greater than 1, when you're getting bigger, you're moving away from the center of dilation. So it shouldn't be on this side. You're going away from the center of dilation. You're increasing the distance between the center of dilation and the pre-image point. So you're making this distance more. So it's going to be over here. So I'm going to just measure, pick up my compass, and that's easier for me on the computer. Okay, I'm just going to measure between point A, and I tried to get it on point A. It's kind of hard on the computer, so yours will be more accurate than mine, and point X. Put a little arc to show that I measured. Mine wasn't super accurate. Let me try to get that a little bit better. Oops. As I mentioned, this is very hard on the computer. I think that should be a little bit better. Not perfect. Okay, and then all I'm going to do is just double that distance. And that's it. That's point X prime. We doubled the distance that it was from the center of dilation. I'm going to do one more, and then you can do the other one on your own. Same exact process. Let me grab my compass. I'm going to put it back on the center of dilation. And I'm going to match up as best as I can to point Z. And then I'm just going to double that distance. And that's our point Z prime. You just need to find point Y prime. And then you can connect your 3 image points together to make the dilated triangle. For the next one, I'm just going to take a second and graph the quadrilateral. And the first transformation that we're performing on it is a rotation of 90 degrees. And remember, it's always counterclockwise unless it specifically says clockwise, and it's always centered at the origin unless it specifies otherwise. So we are going counterclockwise, so we are going this way. So this should move from being in quadrant number 3 to being in quadrant number 2. It should also turn onto its side. Let's take a second and let's do this rotation. I should probably use a different color for this. We have H prime. Now just 2 more, M and A. And now just to connect it together. Oh no, my pieces are flying. It went off of the line segment thingy. There we go. Okay, so now we've rotated it. And now the last thing I need to do is reflect it over the line x equals 1. So the line x equals 1 is this line here. So all you need to do is take your pre-image point, after the rotation, of course, from the shape, count to the line, 1, 2, and move it 1, 2 on the other side of the line. I'll do m prime as well. Oh, I should call this double prime. 1, 2, 3, 4 to the line. 1, 2, 3, 4. All you need to do now is do the same thing with A and T. Count to the line and move an equal number of spaces to the other side of the line. Remember to actually write down your coordinates. So you should write down after the rotation and also your final coordinates after you reflect. Otherwise, you don't get credit for this question. They mark it as no points, even if it's correct in the graph. Graphs are not graded on the Regents exam. Yes, rotations and reflections are rigid motions. They make congruent figures because they keep side lengths the same. For number 11, I'm not going to go through it entirely because I already made a video going over this Regents Review assignment that this is from. So I'm not going to write up the proof, but I will go over the plan. But you can see the Regents Review video, and the plan should help you write it up. So we know that this shape is a parallelogram. Let's keep that in mind. BE is perpendicular to CED. DF is perpendicular to BCD. And we know that CE is congruent to CF. Notice here that we have overlapping triangles. A great strategy for working with overlapping triangles that you learned last semester is to draw them separately. That goes here, that goes here, and those go here. Oh, look! These both have angle C. Angle C is shared. It's congruent to itself by the reflexive property. Whenever you have overlapping triangles, there's going to be something that's shared between them, whether it's a side or an angle. And drawing them separately helps to see it better. And now we know the triangles are congruent by ASA. And since the triangles are congruent, I can then say that BC is congruent to CD by CPCTC. And once I know that BC is congruent to CD, I know that I have a rhombus. And that's because a parallelogram with congruent consecutive sides is a rhombus. You don't have to show all 4 sides are congruent. If you have a parallelogram, it's enough to show that 2 consecutive sides are congruent, and that implies that all the other sides are congruent as well. Once again, for the full proof, please see my Regents Review video, but you should have enough information now to write it up. Make sure in your proof that you also state that you have right angles, and you state that they are congruent to each other. They did not tell us in the givens that we have right angles. They told us that we have perpendicular lines. We concluded from that there were right angles, so it does need to be in your proof.